Good morning, everyone, and thank you for attending this Gleeble webinar. I'm Aranas Jr., and I'm an associate professor in the Mechanical Engineering Department at the University of New Brunswick. And for today's presentation, I'm going to discuss the application of hot deformation processing in hybrid metal additive manufacturing using Gleeble 563 and Simu-Mat 1.0. Now, before I begin my presentation, I would like to acknowledge the support from funding agencies here in Canada, NSERT, NBIF, CFI, MITAX, ACOA, and ECHO Canada. So this particular topic is a PhD project of Kudan Yamuchua, and he's a PhD student under my team. He's collaborating with Dr. Kanwal Chadha and Robert Pallet. Now, in this presentation, I'm also going to discuss the development of Simu-Mat 1.0 developed our team, which consists of myself, Gilbert Pasco is a PhD student, and Thomas McCarthy is an undergrad researcher. Special thanks to Jonathan Lewis and John Pandikan for helping me develop this presentation. And I also want to acknowledge our academic collaborator, Professor Mohammed Jahazi, and our industry partner, Voselfin Additive Manufacturing Center. If you want to know more details about our team, you can visit this website, admtrl.com/team. Now, this is going to be the outline of my presentation. So first, I'm going to discuss metal additive manufacturing. And then I'm going to jump to the second topic, which is hybrid additive manufacturing of M789 and N709 alloy system. So we're going to print M789 on top of N709 substrate. Third one is mechanical and microstructural properties of this alloy system here. And then we're going to discuss the high temperature mechanical response from Gleeble 563. And based on this mechanical response, we're going to use those data to form constitutive models using Simu-Mat 1.0. And then finally, conclusions. So let's now first start our discussion on metal additive manufacturing. And I know all of you are familiar with different classification of forming process. So we have, for example, formative, subtractive, and additive. If we talk about formative process, it's related to, let's say, forging, rolling, extrusion, and drawing process. Now, if we talk about subtractive, it's more related to removal of material or machining. So we have bulk material, and we remove certain sections of the material to form our part. Now, for additive, we are forming our part by depositing the material layer by layer in order to obtain the final product. Now, if we talk about additive manufacturing, or sometimes they also refer to it as 3D printing, it's part of the Industry 4.0 initiative. And for us here in Canada, this is an opportunity to shine for Canadian manufacturers. So if we look at the details of Industry 4.0, there's a lot of aspects. So we can, for example, talk about smart sensor, big data analytics. We can have, let's say, cloud computing, mobile devices. We have IoT platforms. But since I'm a materials engineer or scientist, I am particularly interested with 3D printing, which is related to manufacturing of parts. Now, if we talk about additive manufacturing or 3D printing, there's a lot of advantages and disadvantages. So I will not go into detail, but if you think about additive manufacturing, you can just imagine that I can have my CAD model, and then I can print my part, and then I will have my final product. Another thing is I can print complex parts. So just imagine, for example, in this picture, we have lattice structure, which is difficult or impossible to manufacture using conventional processes. So now, by using additive manufacturing, I will now be able to print or manufacture this lattice structure. Same thing for this particular product right here. So you can see there's an internal details that needed to be manufactured, and this is all possible by means of additive manufacturing. So we have customization, we have little lead time, we have few constraints, and also high materials utilization. So we only use whatever we need in order to form our final product. Of course, there's some limitations to that, but we are not going to cover that portion of the topic. Now, as a scientist, we're always looking for ways to improve the product or improve the process. So that's why we have disadvantages. So it's a slow process, and surface finish could be problematic, and there are some materials issues. And since I'm a materials engineer or scientist, I'm more particularly interested with material issues, which we are going to talk about this later. Now, we have different families of additive manufacturing according to ASTM International. So we have 7. So let's say we have binder jetting, we have directed energy deposition, material extrusion, material jetting, powder bed fusion, sheet lamination, vat photopolymerization. Now for this presentation, we are going to discuss powder bed fusion process. And what is powder bed fusion process? So this process uses thermal energy from a laser or electron beam to selectively fuse powder in a powder bed. Now, if I'm going to play this animation right here, you can see how the process works. So this is our powder bed. So we have a roller assembly. So the roller assembly pushes a certain thickness of powder, and then the laser will melt those powders until you form your 3D part. Now, as it melts, the platform will move, and you can see that's our final product. Now, here are the example of those printed parts, and you can see this is from GE, and this one is your lattice structure, and this is just another schematic diagram of the process. So that's a powder being pushed to the powder bed, and you manufacture your part layer by layer. And you can see in the video that's the actual part being formed. Now, if we look closely at the details of this process, we have a laser, and the laser melts our powder, so we can estimate the volumetric energy density by looking at different parameters in LPBF process. So some of the parameters are laser power, scanning speed, hatch spacing, and layer thickness. And you can see laser power, it's just the power of this laser. This scanning speed is the speed of the movement of your laser. Hatch spacing, this is how your speed moves from one point to another. And we have the layer thickness, and this is the thickness of the powder you deposited on your bed. And you can see, for example, here, that's a computer simulation of the process. So that's a laser moving, that's the powders being melted. And let's just play this video right here, and this is an actual image of the process. So now this is the actual printing, so you can see so you're kind of welding a material layer by layer. Now once you perform LPBF process, how can you determine if the process is successful? So you have to measure the relative density of the product. Now, of course, it depends on the application. Some application will require some porosity, but in our case, we are particularly interested with the highest density possible, lowest density or lowest porosity possible after the process. And this is an example of the equipment. So this is EOS M290 machine. Now, if we talk about the process itself, so we are melting the material cools down. So the cooling rate in the LPBF process is approximately 10 raised to 6 Kelvin per second. Now, if you talk about this cooling rate, this could be problematic for some materials. So for LPBF, you cannot just pick a material and you would expect that it would behave properly when you perform the laser powder bed fusion. And this is because of its high cooling rate. So for example, we have steels. And most of the steels relies on carbon content to achieve excellent tensile strength. And you can always refer to phase diagram whenever you want to check the effect of adding carbon. Now, if you talk about carbon content, if you're going to print, let's say, a steel with high carbon content, because of this cooling rate, once it forms carbides, it can induce some cracks into your material. So that's why it's difficult to print high carbon steels using additive manufacturing. And the solution to that is to print materials with less carbon, but at the same time will have high mechanical properties. And that's where Mar aging steels comes into play. Now, if you talk about Mar aging steels, they have a low carbon content, and their mechanical properties is dependent on precipitation and not exactly on carbide. So you can print your part with a very less amount of carbon to avoid cracking due to carbide formation. And then I can just do aging process in order to form precipitates that strengthen my material. Now, that's why when you check the literature of metal additive manufacturing, most of the time you're going to see more aging type steels in the literature. So, but the thing is, again, we're looking for problems that we can solve to improve our product. And if we check more aging steel, the problem is it has low corrosion resistance and stability at high temperature. And that's why what we're trying to solve right now in additive manufacturing. So our group partnered with industry in order to help them in developing alloys. So for example, Voselfin Additive Manufacturing Center in Mississauga, Ontario, they are working on new alloys that they develop, and we are assisting them in terms of determining the optimum condition in order to post-process their 3D printed parts. Now that leads to the research focus of our group, which is to develop and characterize new materials that are compatible with the laser powder bend fusion technique with superior mechanical properties. And just to give you an idea of the current alloys that we are currently working on, so we have this particular list right now, but for this presentation, we are going to focus on hybrid M789 and 709 steel. Again, M789 is the 3D printed, and 709 will be the conventionally manufactured or substrate during the process. And our work is mostly in collaboration with Voselfin Additive Manufacturing Center, and we are also collaborating with CanMet Materials Natural Resources Canada, which is my previous organization before I joined the University of Brunswick. Now, let's take a look at the M789, but before that, let's check the two most common materials in metal additive manufacturing. So let's check MS1, which is Mar aging steel, and this is the composition of our Mar aging steel. We have nickel chrome moly, we have cobalt, and we have this alloying elements, and you can see they are all low carbon content. Now, if you look at 316L, which is known for its corrosion resistance, you can see high chromium content. There's no cobalt, and there's silicon. There's also low carbon content. Now, for M789 and Corax, which are alloys developed by Voselfin, and we can highlight it here. So you can see M789, there's an elevated amount of chromium compared to Mar aging steel. And you can also see the addition of aluminum in order to induce some precipitation. And you can see that M789 and Corax steels combine the printability of Mar aging steel and the corrosion resistance of stainless steel. So that's why we are trying to kind of get a balance between the strength and corrosion resistance of the material after 3D printing. Now that you now have a background about metal additive manufacturing, let's go to the hybrid additive manufacturing of M789 and 709 alloy system. So before printing, we have to check our powders. We want to be on a certain range of powder sizes. So this is an SEM image of the powder. And if you check the size of the powder, it's between 20 to 50 microns, which is our target range. And if you look at the composition of the alloys we're going to use, again, the powder will be M789, so that's the chemical composition. So it's a cobalt-less Mar aging steel. And if you check the substrate, that's N709, that's wrought state material, so that would be the chemical composition. So N709 is actually your 13.8 precipitation hardening stainless steel, just for a reference, so that's 13 and 8. Okay, let's now go to the LPBF of M789 on N709 substrate. So we use EOS M290 LPBF machine from Voselfin Additive Manufacturing Center in Mississauga, Ontario. So it uses a fiber laser of 400 watts. And if you are interested about the parameters we used during this study, you can check out our publication in MSEA. It's published early this year. So it's this one at the bottom. And the way it worked for our process is this is the powder feed supply, and this is the build chamber, and this is the roller that pushes the powder from one container to another. And then once we push a certain thickness of the powder, you can melt that using laser. The build chamber moves down, deposit another layer until we form our part, and this is the cube that we manufactured for testing. So you can see this is M789 and this is N709 substrate. And again, M789, it's LPBF fabricated, N709, it's conventionally manufactured wrought state. Now, if we talk about this process, one common concern that you can think of is what's the integrity of bonding between M789 and N709. So that's the aspect that we're going to check in the later slides. And another question is, what would be the application of this hybrid alloy system? So let's go to the next slide. And one common application is, let's say, printing of molds and dies. And that's really something significant in terms of additive manufacturing, because if you talk about dies, you can print, for example, conformal cooling channels inside, so you can increase the heat dissipation during the process. So now in our case, for hybrid additive manufacturing, instead of printing the whole die using 3D printing, we can just, for example, just use a conventionally manufactured metal piece, like for example this bottom part, and print all the complex features on the top of this material. But again, the question is, would it be reliable or not? And it's not just limited to die and mold. You can use, for example, to repair some components, so and print something on top of that to fix a failed part. Now for this study, we're going to use two types of sample. Sample number one, it's as fabricated, so this is after printing. And sample number two will be directly aged at 500 degrees Celsius for 3 hours to induce precipitation. Now let's go to the third part, which is mechanical and microstructural properties of our hybrid alloy system. And this is the M789 side. So this is the printed part, so we are analyzing the M789 section of our material. So now, as you can see from this image, we have the overlapping melt pool boundaries, which is very common in metal additive manufacturing. So those are the melt pools, and those shapes depends on the manufacturing parameters, and this melt pool boundaries is also a result of the heat dissipation during the process. And you can imagine it's highly dependent on the building direction. So you are building, for example, from this side to from bottom to top of this image right here. So these dimensions, you can also create a lot of study based on the dimension of the melt pool. So you have the width of the melt pool, depth of the melt pool, and those information. So now looking at the TD2, TD1 direction, which is this one, so that's the top of the sample, you can see those are the scan tracks. So this, you can see how the laser moves from one position to another, and you can see it from this image. And again, that's very common for additively manufactured part. So now we're talking about M789. Let's go to the interface in order to check how it looks like. So if you look at the interface, you can see in this image on the top leftmost image, so you can see that's the melt pool boundaries, that's the interface, this is your N709 substrate, which is conventionally manufactured. And if you look closely at the SEM image, let's say in the M789 side, you can see those are the melt pools, and you can see some of the cellular and dendritic microstructure, and the alignment of this is is highly dependent on the heat dissipation during manufacturing, so it's highly dependent on the building direction. And if you move closely to the interface, so this is the interface section, you can see those are your additively manufactured component, and this is your conventionally manufactured components. So there's a fusion between those two materials, and this is as printed. Now, how about after heat treatment? Now, in the literature, most of the heat treatment after additive manufacturing is done in order to remove, let's say, this melt pool boundaries. But in this particular case, we skipped the solutionizing part to remove this one, and we went directly to aging at 500 degrees Celsius for 3 hours. So that's why you can see some traces of melt pool boundaries, but not as clear as the one from as printed. And you can see those are the melt pool boundaries, so it's still kind of visible. And then you can see the interface between the M789 and N709. Now, now that we know how the interface looks like, we also perform testing. So we perform nanoindentation across the interface from N709 side, going to M789 side. If you look at the as printed side, you can see N709 has around, let's say, 650 Vickers hardness. And now once it crosses the interface, you can see a huge drop in hardness. And now it becomes 500 Vickers hardness for M789 seed. So again, this is as printed. Now if you go to the heat treated, which is aged for 3 hours, you can see a different profile. You can see from N709 side, you can see around 700 Vickers hardness. And as it crosses the interface, you can see there's no drop in terms of hardness. And you can see now the hardness profile becomes more homogeneous from N709 to M789 side. So there's an animation here. Oops, let's try that. Oops, it's not working. Okay, so this is the part that we kind of analyzed. So now if we just change my pointer, so move to the next one. So what we did is based on this material, we kind of machined a tensile sample. So you can see if this is for reference with the center as our interface, and you can see those samples right there. So we performed tensile in order to check the integrity of the interface. Now, interestingly, the material didn't fail along the interface, and you can see it from the top section here. As printed, it failed on the M789 side, so that's M789. The interface is somewhere here. And after heat treatment, it failed on the N709 side. This shows that by doing heat treatment, I can adjust my tensile strength, my ductility, in order for me to design my mold where it will kind of fail once it passes its mechanical properties. And you can even see the stress strain curve before and after heat treatment. So this is as printed. That's heat treated material. Basically, if you check the properties, it's reasonably ductile because it has more than 10% of elongation, at least for more aging type steel. This ductility is still it's quite good. And you can see for from the SCM micrographs that it has the typical cup and cone features of ductile fracture, and you can see it right there. So now we're also interested in how the interface looks like in terms of, let's say, the dislocations, in terms of faces. Now if you look at the EBSD image of the as printed material, which is this one, so this is M789, that's N709, that's your interface, and we check for maximum texture intensity, and this is all below 2, which means that the orientation, it's mostly random, or it's considered as random. Now we also measure the kernel average misorientation in order to check to assess the dislocation density. And in this particular case, 44% of this particular grains has misorientation of 2 degrees and above, which means it has a higher dislocation density, which is pretty common because this, again, this is 3D printed. You have high cooling rates during the process, which means that you will induce a lot of dislocation density. Now from the cam maps, you can see this is a face map. In the M789 side, this is fully martensitic, but if you look at the N709 side, you will form some austenite face or FCC face, and you can see those yellow section, and those are basically for this particular image, this is below 1%, around 0.3% to be exact, and you can think of it as a noise, but we check it via XRD, and we validated that it is indeed austenite or FCC face. Now after heat treatment, you can see some of the grains. So this one below here, the grains is much larger compared to the 3D printed ones. We check the crystallographic texture, similar to the previous one. The maximum texture intensity is below 2, which means, again, that you can consider it as isotropic, or you have random orientation. We check the cam maps, and from the cam maps, we saw a significant decrease in terms of misorientation of 2 degrees and above. Basically, the drop is from let's say 44% to approximately 8%. And you can see it from the image here. You have the blue section, which has a misorientation of close to 0 degrees. Now, if you look to the phase map of after heat treatment, again, M789 side, it's still fully martensitic. You go to the M709 side, you can see traces of FCC austenite. When we measured it, it's approximately 1.5%, below 2%. And again, we confirmed everything via XRD, and it's really austenite. So as much as possible for this particular process, we want to limit the percent of austenite because we are using high temperature processing, and austenite can be detrimental if we have high temperature applications, especially for mold and die. Now, since we perform heat treatment, it's not just about texture, dislocation, and phases. It's also a matter of, are we forming another phase or precipitates, because we're doing aging. In the M789 side, you can see this blue line, so that's your ETA precipitates, and we're going to analyze that shortly. And on the N709 side, we are forming the FENIAL precipitate, which is this one, and it's also called beta precipitates. So that's a section that we kind of analyzed there. Now, looking at the interface, we also measure the change of chemical composition, especially the titanium, because if you check the chemical composition, N709 has almost no titanium, but if you look, for example, at M789, there's around 1% of titanium, and you can see it from there. Now, we use EPMA in order to determine the profile, and once we get the profile, we kind of run a thermodynamic simulation in order to estimate the amount of precipitate we are forming based on our aging process. And you can see that the amount of precipitate changes from N709 to M789 side. So you can see that this would be the approximate thickness of our interface layer. Now, using high magnification SEM imaging, you can see those white particles, and you can see this micron bar is around 4 microns. And those precipitates are from M789 side. We're analyzing, and you can see we perform EDS, we track titanium, there's aluminum, there's also some nickel in some sections, but we also perform a higher resolution EDS, and you can see here that we are forming some titanium type precipitates, there's some nickel, there's also a kind of aluminum. Now, since we want to analyze it further, because this is a new alloy system, this is M789, we performed atom probe tomography in collaboration with Deakin University, with our colleagues there, Dr. Thomas Doreen and Dr. Lu Jiang. So this is the results of atom probe, and you can see spherical precipitates, the size is approximately 5 nanometers. You can see this precipitates right here, and this is the composition. Now, it's not just spherical precipitates. We also found some rod-like precipitate in the atom probe tomography, and this different size or morphology of precipitates is of course dependent on the amount of dislocation density that was generated during the LPBF process. So that's why we have those two types. So basically, that's our results in terms of characterizing our interface. Now let's go to a more interesting topic, which is high temperature mechanical response from Gleeble 563. Now we're going to discuss also the development of Simu-Mat 1.0, and the results are published in MRS Communication. So now if we talk about a high temperature deformation process, so if you know my research area before I joined UNB, if you're following some of my research, I'm mostly doing thermomechanical processing, high temperature deformation, and I'm looking at phase transformation, specifically dynamic phase transformation, formation of ferrite by means of deforming austenite. And when I joined UNB, I had an opportunity to be involved in additive manufacturing projects, and that's where I tried to find a synergy between thermomechanical processing and additive manufacturing. And if you think about it, whenever there's high temperature application of parts, we can use, for example, thermomechanical processing concepts in order to simulate the high temperature application. So in this work, I'm going to show you how we kind of use the thermomechanical concepts in order to support the additive manufacturing. But the first question is, what would be the application of this additive manufacturing and how it would relate to high temperature processing? So if you're following additive manufacturing, there's a lot of positive developments in terms of this technology. So one of the news, you can read it from here: Pepsi saves 96% by 3D printing bottle molds. And this is the bottle molds that they're referring to. So those are the bottle molds. And once you talk about, let's say, the mold temperature can change. It depends on the material that you are going to fabricate. And you can see it from this table here. So this is, for example, the material to fabricate. We have plastic, zinc, aluminum, and copper as an example. And you can see, based on those material, we can see the temperature range of the mold during the process. So for plastic, it could go from 65 to 175. If we have a copper, let's say, the mold temperature can go up to 300 to 600 degrees Celsius. So steel die mold application can reach up to 1000 degrees Celsius, and you can see it from here. So that's why in this particular work, I'm going to show you our high temperature processing up to around 1000 degrees Celsius. Now, it's not just limited to mold. So let's say if you're talking about aerospace application, and if you are attending lectures on, let's say, alloy design, this is probably one of the most common figures that you will see. So this is a Rolls-Royce Trent XWB. So it's a jet engine, and if you talk about jet engine, you can discuss different parts. So this is your front exhaust fan, that's your static and dynamic blades, that's your compressor, that's your turbine. And if you look at this jet engine, the working temperature changes from front exhaust fan to turbine. And that's why that change in temperature will lead to the change in terms of materials design. So you have titanium is normally used as an exhaust fan. And if you look at, for example, the turbine section, it's mostly consists of nickel-based alloys. Now, since in additive manufacturing, since the material properties are not yet established, so if you're going to 3D print a part, let's say for aerospace application, if that part gets to a certain temperature, it would be important to get its high temperature mechanical behavior in order to make sure that it would not fail while it's in service. So going back to our work, so this is the thermomechanical schedule of that we're going to use. So we are going to heat up the sample at this rate, go to 1150, hold for 3 seconds, go down to deformation temperature from 850 to 1050 degrees Celsius, deform the material at a strain of 0.7 and at a strain rate of 0.01, 0.1, and 1. Now, in this work, we are going to separate the testing from on N709 and M789. So you'll see it from this slide. So if you look at this material, we machined compression samples at N709 side. We machined another compression samples from M789 side, and we tested them separately. Now, we test them separately because we want to establish constitutive models on those both materials so that once we run FEA, we are sure that our values are accurate. So this is N709, and this is as printed AP. So this is before our heat treatment. So we have different strain rates at different temperatures. M789, again, same temperatures, same strain rate. And what you can see here basically is, as you increase the temperature, of course, your stress will drop. As you increase your strain rate, your stress will go up. And same thing for heat treated. You will see the similar trend. And we're not going to discuss all the mechanisms involved after deformation. And so let's say we can have dynamic recrystallization, dynamic recovery. That's part of our future study. For today, we are going to focus on stress modeling of our material. Now, in general, we are just looking for trends. So if we talk about, let's say, those stress strain curves, so the increase in temperature results in decrease in flow stress of the materials, which is pretty obvious. And the second item here, it's also obvious. An increase in strain rate leads to increase in flow stress of the materials. And the only question is how the how the material will behave if we increase or decrease the strain rate. So how can we quantify that change? And the way it works is we can establish constitutive models in order for us to establish how those stresses will change based on temperature and based on strain rate. And as you can see on this table that we have different models. So these are the most common models. So let's say we can have Hensel-Spittel model, we have modified Hensel-Spittel, we have Johnson-Cook, modified Johnson-Cook, we have Zener-Hollomon, we have Zerilli-Armstrong, we have modified Zerilli-Armstrong. And we have some of the primary theoretical basis of this particular models. And these are all the equations. Now, we are not going to discuss the details of this equation, but in our work, we can calculate all of these constants and we can model all the stresses involved. So for example, this Johnson-Cook model, you have A, B, and N and M. So you have all those constants that we can calculate in order to model the stress. Now, since the target application is in the mold die where temperature can increase up to 1000 degrees Celsius, it is essential to model its high temperature properties, and that's what we're going to do by means of constitutive modeling using Simu-Mat 1.0, and this is a software we develop in our lab. So this is the flow chart of our app. So we have input, and input comes from the data supplied by the Gleeble 563, the stress strain curve. So we feed that to our app, but it's not just stress strain curve. You have to define some of the properties. So let's say you have to know your melting temperature, yield strength, Hall patch constant, grain diameter, and strengthening coefficient. Now, once you know all those numbers, you feed that to our software, and you can establish constitutive models. Now, in our software, we have three different types. So we have phenomenological, we have physical-based, and we have an artificial intelligence-based. Now, based on this, we can calculate the constants from the equation I showed you in the previous slide, and we can use that, let's say, for FEA analysis to accurately measure our stress while it's in service. So the app can calculate, for example, or can model the stress behavior, and you can see it from here. So experimental versus the theoretical stress strain curve or simulated stress strain curve. And we can also generate contour maps in order for us to determine the most accurate region or at certain temperature and certain strain rate where the models would work perfectly. Now, our lab is working with this app, and you can visit this website right here to know more details. But basically, this is module 1, and this is up and running right now. We are currently working on module number 2, which is related to parameter optimization. Now, let's look at how the application works. So this is a demo by Thomas McCarthy, who's a researcher in our lab. He's working with us probably for almost 2 years now. So this is the app Simu-Mat. So if you're interested in demo version, you can email us at ad.mtrl@unb.ca. And we're also thinking of organizing a workshop regarding this and its function soon. So if you're interested, please send us an email. So now it's loading. Okay, so this is the interface of the app. So we have stress strain curve. We have a particular template wherein you can put the stress strain curves from Gleeble 563. And once you put that in a certain template, you can just upload it in this app. Now you can see Thomas already uploaded the file, so you can compare, for example, stress strain curves at different temperature, different strain rate. And you can also perform, let's say, filtering of or smoothing of your curve. And if you're working with Gleeble, you know that there are some small fluctuations in Gleeble because of its accurate measurement. So you can use filter to smoothen that curve. You can even apply interpolation to get a certain number of data points at a particular strain range. And you can see this is strain range of 0.1 to 0.7. And Thomas picked only 10 data points for now. And now this is the Constitutive model tab. So he just clicked that tab, and in that tab you need some of the constants. So for example, A is your yield strength. You can calculate your yield strength using the app itself. So there are some small function inside this app. So now he calculated the yield strength. You have to know your melting temperature. You have to define reference strain rate. So you can see all of this are in the app. And you can see from Johnson-Cook, there's an estimate AARE, or the amount of error, or relative error based on the models. And I can save my figures, or I can also acquire figures associated with the calculation of constants. So you can see we are only showing the final results, but if you want to track the entire process of Johnson-Cook, or let's say modified Johnson-Cook, once you save your figures, it will generate all the steps, and you can see it from here. So Thomas is navigating to that folder. You can see different figures, and we have documentation for that. What does it mean? What are those figures? And he's going to open one of those for sure, and here it is. So you can see that this is the calculation of C coefficient, and you can, for example, have the plot of experimental versus simulated curves, and you can have, let's say, your contour plots that shows the amount of errors. So now after, and you also have the Excel file that contains your constant. If you want to manually plot them, you can have those constants, or if you want data points for each plot, it's also available in the Excel file. Okay, so now you have those information from the app, and Thomas will later show you that you can perform optimization as well. So before that optimization, so this is changing, manually changing the constant of Johnson-Cook, and you can see that if you don't trust those values, you can manually adjust it and check how it would affect your error. And you can also compare one model to another. Let's say this is Johnson-Cook and modified Johnson-Cook, and you can compare them in a single plot at a particular temperature, at a particular strain rate. So you can see that. And if you so he now goes back to the constitutive models, and you can optimize it. You can see right now it's 11.69. The error goes down to 6.67. Now we understand that sometimes you don't want any optimization techniques performed, but in this case we have you have those options. So again, you can compare the different models in a single plot. I think it's coming to an end. And we haven't integrated the neural network based models, but everything is done. It's just really putting it inside this interface. So I'm also going to present some of those results later in the presentation. And that should be it. So again, if you're interested, feel free to send us an email at ad.mtrl@unb.ca. So now we have the Gleeble data stress strain curve. We feed that data into our app, and these are the results. So now you can easily get this within probably 5 minutes using our app. Now you can already determine which model gives you a more accurate result. So for example, this is as printed N709 M789. This is heat treated, and you can see the one highlighted in green. That's the lowest error that we calculated for N709 as printed. Now the red one, it's the worst one, which is, you can see Johnson-Cook gave the worst fitting for all the models. And for example, here M789 as printed, that's Zener-Hollomon. This is also Zener-Hollomon, and this is Hensel-Spittel. So now, based on this app, it's just convenient. I can just drag all my data. I can identify which models to use. So let's take a look at the Johnson-Cook model, and that's the worst. And I want to show it because even though that's that's marked as red, you can see that if you compare the experimental and the simulated curve, it's still quite good, to be honest. So you'll see that it still kind of mimics the experimental data to some extent. And if you generate contour plots, there's still some good sections really here. And so this is for Johnson Cook, so that's AARE. And for example, if we use Zener-Hollomon, and this is as printed, that's heat treated, and you can see in Zener-Hollomon, it's quite good in terms of comparing the experimental and simulated stress strain curves. So they are very close. The AARE, it's less than 5%. So this mimics the actual process. Now, how can we use those models? So we can feed those information to our FEA software in order to have an idea what's happening to our material during in service, specifically at high temperature. And this is still an ongoing study of our group. So this is an ANSYS simulation, and again, this is an ongoing. We don't have extensive results yet, but you can see that some of the results will make sense. Now, we only use Johnson Cook modeling just for the sake of showing that the model works. So this is room temperature. You can see this is as printed, and we applied a certain amount of stress, and you can see the stress concentrations are in the M789 side, so right here. And after heat treatment, after aging for 3 hours, you can see the stress concentration are now towards the N709 section here. Now, the interesting part is once we go to high temperature, and that's the one we want, that's why we did those modeling, that's why we use Gleeble, we want to check what would be its behavior at high temperature. And in this case, we picked the 850 degrees Celsius, and this is the behavior of our as printed material. And you can see that the stress concentration could be on the top or bottom, so it's fairly homogeneous across the length of the samples, which means that it could either fail at N709 and M789 side. And after heat treatment, same thing that you can conclude, it's fairly homogeneous, so there's no weaker section, or you can treat it as they are behaving homogeneously from one side of the material to another. Now, we are still working on this one, so we will verify all the results by means of high temperature testing, compare it with our models to make sure that everything is accurate. And really the application is, let's say, if you have a mold, you want to check how it will behave at a certain temperature, a certain amount of stress, we can use those models. Now, in this particular case, we use phenomenological and physical-based models, but in our app, we can also do some artificial neural network constitutive modeling, although this is not that practical, at least yet, because it's difficult to implement it in finite element analysis. So I think it's also good to show what we are currently doing in terms of A and N. So for A and N, we have different layers. It consists of input, hidden, and output layer. And for our input layer, this is basically our data set from Gleeble 563. We have strain rate, and temperature. And we have those hidden layers, and we have the output layer, we have our stress. So that's the number that we want to obtain the stress values. Now, this is the flow chart of the entire process of this particular A and N model. So we have the generation of data, which is from our Gleeble 563. We determine a sample size, in this case 50. We determined a certain neuron range, so from 5 neurons to 25 neurons, we run our models in order to check how would the number of neurons affect the fitting. And after getting results from our ANN, we remove the outliers by using the criteria 1.5 of the interquartile range. And after removing the outliers, we perform statistical analysis to measure the generalizability of the model that we developed. So we use pairwise Welch t-test, and we also use the Holm correction, and that's where we got our optimal range. Now, more specifically, if we look at the curves, this is how we did that. So this is M789 as printed. We have 15 stress strain curves. So 14 of that curves, we use this as a training data. So that's what we use in order to develop the models. And we remove one stress strain data, And that data, we use it as our testing data. And how can we measure the performance of our neural networks? So the first approach is to calculate the absolute error obtained from the testing data, which is from this green line. So we measure the AARE by just using this green line. And we also have AARE obtained from the entire training data. So instead of using this green, we all use the 14 stress strain curve and get the average AARE that we obtain. Now take note that ANN-based constitutive modeling is also available from Simu-Mat with the selection of training algorithm. In our case, we use the LM algorithm right here and specified in the slide. So let's look at the results. So we run again from 5 to 25 neurons. I'm only showing 5 to 20 right here. And you can see the green is the AARE calculated using the training data. And you can see once I've used 5 neurons, as I increase the number of neurons, I'm decreasing my AARE. Now for testing data, it's quite tricky because if you talk about testing data, again, we are testing outside the range of our data set. So you would expect that the error would be quite significant. And you can see those variance measured from our models. Now, if you look at this particular plot, so this is after 30 neurons, we have a specific relative AARE for training and testing data. Now, we specifically identified 13 because based on our statistical analysis, more than 13, it would not be accurate. So it's written right here. So increasing the neurons in the network beyond 13 decreases the generalizability of the model. Beyond this range, increasingly poor generalization is observed and therefore should be avoided. Now, if we look at the AARE after 30 neurons, if we check the training data, it's only 0.31%. Again, if we check the process of calculating AARE from the previous model I showed, it's actually your training AARE. And this is extremely low compared to what I showed you earlier. So this is really close to 0. Now, if you look at the AARE, and again, this is AARE obtained from the data that we didn't use during testing. So this is outside range. And our AARE is 5.77. This is quite decent for this model, since this is outside the range of our data set, and still we are getting 5% AARE. And for us, we feel that this is still quite good for this model. Now, as a summary of that of Simu-Mat 1.0, again, we have 3 different applications. If we talk about formative, if you're forging, rolling, and if you, for example, want a constitutive model associated with that, we can use Gleeble 563. We can use that information, feed that to our app. We can develop models as quick as 1 week, for example, including testing if everything is machined. Now, if we talk about subtractive, it's high strain rate deformation. It's a shearing process. We have split Hopkinson, high temperature, so we can do up to 600 degrees Celsius testing. We can generate stress strain curve from Hopkinson, and we can generate models for associated with machining process. For additive manufacturing, we are mostly doing simulation of in-service application for FEA, so we can do high temperature testing if you think your part, let's say, requires high temperature environment. So we can establish the material constitutive models for new alloys for as quick as 1 week. Includes mechanical testing. This includes comparison of models to ensure accuracy. Now, let's go to the conclusions of this work. Now, the first conclusion is a strong metallurgical bond is formed between the M789 and N709 steels by LPBF process, as evidenced by the fact that the material fractured either in the M709, in the as printed, or N709 in the directly aged during tensile testing and not on the interface. And second is a fracture of the as printed material on M788 part during tensile testing may be attributed to the strengthening of the beta precipitates in the wrought N709 section before heat treatment. The failure of the heat treated material on N709 part may be due to the formation of the austenite phase in the M789 section, together with the precipitation of the eta phase during heat treatment, which strengthened the M789 section. Now, third is the hardness of M789 section after heat treatment was considerably increased due to precipitation strengthening, while that of the base N709 section is essentially not changed. Now, it is well known that constitutive modeling of alloys has been instrumental in the thermomechanical process such as hot forging, rolling, and machining operation, and this work showed the potential application in metal additive manufacturing, but not in manufacturing parameter optimization. It's in simulating the in-service stress condition of the AM ports. And finally, a data analysis tool, Simu-Mat 1.0, has been developed to conveniently establish practical constitutive models from stress-strain data while comparing AAREs to assess accuracy. So it can be employed in formative, subtractive, and additive. And the results, again, it's published in MRS Communications if you are interested. Future work, we want to determine the stress behavior at different temperature range. We want to do tensile. We want to do in-depth microstructural analysis, looking for dynamic recrystallization, for example. And we are also adding some of the models to our Simu-Mat 1.0, and we are going to release some of the updates related to LPBF parameter optimization using the app. And thank you for attending this webinar, and if you have any questions, just let me know. Thank you.